we have our Laplace transform table. That looks like this. Going forward is pretty easy. Like, say, for example, we wanted the Laplace transform of some polynomial, t to the n. Then we would just use this. So the Laplace transform of t to the n is n factorial over s to the next exponent, n plus 1. So, for example, the Laplace transform of t to the 7th would be 7 factorial, whatever that is, figure it out, over s to the 8th. That's pretty simple. What about going backwards? There's an old math joke. It's a terrible joke, and I've probably told it to you guys before, but I'm going to tell it again. You've got 3 pots, and you've got a flower. And right now, the flower is in the middle pot. You ask a physicist, a mathematician, and an engineer, how do you get the flower from this pot to this pot? Everybody agrees you go to the right one pot. Everybody agrees on the solution. Move the flower 1 pot to the right. Now you hand all 3 a different problem. I've got the flower over here and I need to move it over here. The physicist and the engineer both say move it 2 pots. The mathematician says no, move the flower over 1 pot. Why? Because now we've turned it into a problem we've already solved. It's a terrible joke, it's not very funny, but that is the key to most of DE. When somebody hands you a problem you don't immediately know the answer to, turn it into something that looks familiar. So if I wanted the inverse Laplace transform of 1 over s to the 9th, I'm going to use this formula that the Laplace transform of t to the n is n factorial over s to the n plus 1. I'm going to make this look like this. So I'm going to think, oh, well, that's n plus 1, so n here must be 8. So in order to fit this pattern, I want to write this 8 plus 1. I need an 8 factorial here that I don't have. Well, the way to get it there is multiply and divide it. So I really want the inverse Laplace transform of this. Inverse Laplace transforms are linear operators, meaning we can pull constants out. So this is 1 over 8 factorial, the inverse transform of this. Now we fit the pattern. It looks like that. This is t to the n. So 1 over 8 factorial t to the 8. It's a lot like when you're integrating versus taking the derivative. You have to, like with power rule, you bring the power down, but when you integrate, you divide by the power, you go backwards. Same kind of idea. Honestly, for the same reasons. Okay, that one was easy. I'm sure you guys could have figured that one out. But what if we had a harder one? What if we wanted, say, the inverse Laplace transform of 5 over s squared plus 9? Well, we look at our table and find the closest we can find to that. So that looks like this one. I've got an s squared plus something, and then just a number on top, no s on top. Okay, but in order to match this, the square root of what's here must be exactly the same as what's here. So I've got a 9 down here. My k is 3. I need to have a 3 on top. So I'm going to put a 3 on top. So I'm using this formula. equals, what was that? K over S squared plus K squared. I want to match this formula. So my K here is 3, and that's 3 squared. So I'm going to pull that 5 out. I need a 3 on top, so I'm going to put my 3 on top. And at the same time, put 1 on the bottom, so I'm not making stuff up. This is what I want the inverse Laplace transform of. That is sine of 3t. And then I've got this 5/3 hanging out front. Okay, pretty easy still so far. What if I want the inverse Laplace transform of 3s plus 2 over s squared plus 25. By the way, before I forget, if you ever find yourself trying to use this formula here or this formula here, just go through the trouble of doing the partial fraction decomposition. It's more trouble than it's worth. Don't try to use this formula or this formula. Just do the partial fractions and separate it into 2 terms. It's really not that bad. However, the one we're working on, there's no formula that matches that. Don't try to get fancy and try to match up with these. It's not going to work out. We want to use these guys by separating this out. So I'm going to split this up. The s over s squared plus 25 will be a cosine. The 2 over will be a sine. So split this up. I'm going to pull that 3 out. S over s squared plus 25. That's going to be a cosine plus 2. Now to use that sine formula, I need to have a 5 up here. In order to get that 5, I need a 1/5 in there. This is cosine, or we want the inverse transform. The inverse transform of that is sine, or is cosine. The inverse transform of this is sine. So we get 3 cos of 5x. Sometimes we call it, when we were doing this last week, I had t on this side, s on this side. This particular chart I'm showing you uses x and s. That's irrelevant. Don't stress too much about that. Whether we call our regular domain t or x doesn't really matter. So since I've already started writing x, I'm going to continue with x. And this is sine of 5x. Okay, now what if we have something, make it a little more challenging. What if we had, we want the inverse Laplace transform of 3 over s minus 2 squared plus 16. Okay, so that matches something in our chart pretty well. That looks like this one. So that's an e to the at times sine of kt. So k here will be 4, or will be 4. So really not much we have to do here. We got to put in a 4 on top and bring it out, bring the 3 out. So this will be the inverse Laplace transform. I can bring my 3/4 out, put in a 4, s minus 2 squared plus 4 squared. This was e to the a t. A is whatever is after the minus, so e to the 2t sine of k. K was this guy here, also there. Oh, if I'm using, got to be consistent. I'm either using x's or t's. All right, what if something doesn't quite fit this format, but we need to make it fit that format? So here are the hard ones. These are the ones that tend to cause the most trouble. What if I want the inverse Laplace transform of 2 over s squared plus 8x, 8s, minus 1? Okay, this does not fit the format of anything in that table. So what I have to do is make this look like the previous problem by completing the square. In the denominator. So I'm going to rewrite this guy here as s squared plus 8s plus 16, half of 8 squared minus 16 minus 1. So use the first two guys to complete the square by taking half the middle number, squaring it, adding it, and subtracting it out. So that will be s plus 4 squared. And then I got a minus 17. So I'm going to write that as minus the square root of 17 squared. Now I got to look at my chart. That looks like this formula. But I need my k on top. My k was square root of 17, so I need to put that in and take it out. So I'm going to put in a square root of 17 and divide by it. And then I fit my formula. Pull the 2 out and so forth. Okay, so sometimes you got to play around. Sometimes you got to split stuff up and have a sine term and a cosine term. Anytime you've got, say, a linear factor on top, if we wanted the Laplace transform, inverse Laplace transform of, I don't know, 5s plus 7 over, and then we've got some quadratic down here, plus 10s plus 12. Then you're going to complete the square in the bottom, split this up into 2 separate fractions. The s over stuff is going to give you some kind of cosine, maybe with an exponential. The constant over this quadratic will give you some kind of sine, maybe with an extra exponential. Okay, let's actually solve some DEs using Laplace transforms. So let's do the one from the test. The initial value problem we had. This one here, this shouldn't be too bad. So that's y double prime plus 4y equals 4, subject to y of 0 equals 1, y prime of 0 also equals 1. All right, so we're going to take the Laplace transform of everything. So I'm going to write out a bunch of details here. Laplace transform of y double prime plus the Laplace transform of y should equal Laplace transform of 4. Laplace transform of y double prime is s squared capital Y minus s times y of 0 minus y prime of 0. That part was right. That's just the Laplace transform of y, which is just capital Y. So plus 4 capital Y equals 4 over S. Find our y's, get them together. This problem is so much simpler than I was making it. S squared plus 4 times capital Y will equal 4 over S plus an S from right there, that's 1 times S plus a 1. Pull everything over, Y then, just solve that for Y. 4 over S times S squared plus 4 plus S over S squared plus 4 plus 1 over S squared plus 4. Okay, now we want to do partial fractions on this one. This one I can do. That one's not bad. That's pretty easy. That one I could do. That's just a sine of 2x right there. That's a cosine of 2x. But I need to split this one up. I could combine all these into one thing and then do the partial fraction decomposition. But I find it easier just to deal with each piece. If you can already do one, why squish it together with other ones that are difficult? This one we need to split up because I don't have something that looks like this in my table. So I want to split 4 over S times S squared plus 4 into A over S plus B over S squared plus 4. So we get 4 is A times S squared plus 4 plus B. Oh, wait, no, that's not going to work. We need, this is an irreducible quadratic. This one has to be linear. So I need a bx plus c times an s. And I'm trying to find a, b, and c. So I like to just match up. It should be s. I like to match up my front guys. So I'm going to have an as squared and a bs squared. Over here on this side, I don't have any s squared, so those must equal 0. So a is negative b. My constant term, a times 4, must equal 4. So a must equal 1, meaning b equals negative 1. And then my s term, I'm going to have a c times s must equal 0, because there's no s term over here, so c equals 0. So what we get, if my partial fraction was correct, is 1 over s minus 1 times s, so minus s over s squared plus 4. Okay, so that replaces this. So we get y equals, hey, look, those two cancel. Remember, there was no cosine in the answer. 1 over s plus 1 over s squared plus 4. Nobody asked me for capital Y. I want little y. So I take the inverse Laplace transform of both sides. Inverse Laplace transform of capital Y is little y. Inverse Laplace transform of 1 over s is 1. Inverse transform of 1 over s squared plus 4 is sine of 2x. That's the same answer we got solving this using conventional methods, solving this as a non-homogeneous linear second order DE. Okay, so sorry for all that confusion in the middle. In fact, I'm probably going to put in the notes, skip a bunch of stuff. So hopefully you skipped over until this made sense. I'll make a video nice and clean where I do another example.